Hi everyone, I'm Harsh Khatagwar from Applied Cognitive Science Laboratory at IIT Mandi, and I today I would be presenting one of our research work in the behavioral cybersecurity domain. And the topic of today's talk is modeling the effects of different honeypot proportion in our deception-based security. So as we know, cyber attacks are increasing in a rapid manner, and it is nothing but an organized attempt by the adverse enemies to disable the computers or steal the data from the systems present in the network. And it has been steadily increasing across the past decade. And in the recent past, one of the major cyber attacks happened in the cyber infrastructure of Twitter and the Marriott, and which really led the organization to think about in making the infrastructure strong. So these rise in cyber attacks and the lack of security solution has uplifted the research community to come up with some novel idea that can help in defending against the modern cyber attacks. So for these, there exist some security solutions such as intrusion detection system, filtering strategy, deception, and various others. So one such technique is deception. Deception is nothing but the act of making someone believe in the false information, and it may help it may help in real time as a real time solution against these modern cyber attacks. So also, as we know, in the cyber attack scenarios, it is likely that human decisions may be affected by various circumstances and various factors such as complexity of attacks, network topology, network size, probing action codes, port hardening, and various others. So, deception in cybersecurity has been previously studied with the help of simulation games with and without the complete information, as mentioned in the literature of behavioral game theory. So, it has been implemented with the help of honeypots and has proven to be very efficient technique in defending against the cyber attacks. So honeypots are nothing but the fake systems that act like that mimic like the real ones, and it has been used to identify and the divert the adversary from the legitimate target. So for this, we had built our own simulation tool called Deception Game to study various factors that are likely to influence adversarial decision. So deception game is a sequential single play game between adversary and the network, and it is denoted using the notation DG, N, K, and gamma, where N denotes the number of honeypots, K denotes the number of uh, N denotes the number of systems in the network, K denotes the number of honeypots, and gamma denotes the number of probes after which the adversary makes his final attack. So let's look into the DG211 where we have two web servers. One of them happens to be the real and the other is the honeypot which would be acting like the real. And for the no deception means in the no deception condition, when the hacker probes one of these web server, he gets the real response, means the true response from the network. And based upon this, he decides to go for the next another computer. So, however, in the deception condition, when the adversary probes any of the web server, he gets the opposite of what the web server is. Like here, on probing web server 1, he gets the response as honeypot. However, the web server 1 happens to be the real web server. So, based on this, the attacker decides to go for web server 2, which happens to be honeypot. So, as you know, based so today we would be investigating how different honeypot proportion, how basically different presence of different honeypot proportion affects the adversary's decision. So for the experiment, we translated the DG game into 20 web servers, and we across the we had three kinds of condition: small, medium, and the large. So in the small condition, we had 25% of them as honeypot, and in the medium condition, 50% of them as honeypot, and then the large majority of them were the honeypots. So As we know, if there would be increase in proportion, then it is likely that there would be some effect in the decision, and also it would likely be that the adversary would be attacking more of honeypot web servers. Also, as per cognitive theories like IBLT, people try to choose those alternatives that maximizes their blended value, and hence we expect to decrease in the number of attack as there is a rise in the honeypot proportions. So for this, we had in small condition we had 20 web servers, out of which five of them were five of them were honeypot, and the adversary had the option to probe 5 times. And in the medium condition, there were 20 web servers, and out of which there were 10 web servers, 10 honeypot web servers, and the adversary had the option to probe 10 times. And likewise for the large 20, 15, 15. So for the experiment, the dependent variables were regular probe, honeypot probe, and no probe. Likewise for the attack action, regular attack, honeypot attack, and not attack actions. So for the study, we recruited 60 participants from the crowdsourcing website called Amazon Hunter. For each, we randomly divided across the 3 conditions, with each condition having 20 each. And out of 60, 48 were males, 12 were females. Majority of them were from the STEM background, and the average age happens to be 30 years. So this is the web screen for this is the user interface for the DG2055, where five of them are honeypot web server, rest 15 are the real web servers. So here the left one is denoting the 20 web servers, and the adversary had the option to not probe and proceed ahead. And likewise, they were also given with some instruction denoting here. And once the adversary probes one of them, like here, the adversary had probed web server 2. So he probed web server 2 and he got the response it as an honeypot. So he's also shown that you have how many probes you have done, so that means just to inform the hacker. And next, once the adversary probes, he moves to the attack stage. After probing for 5 times, he moves to the attack stage. And in the attack stage, he is again shown with the 20 web servers, and he has asked to attack one of these, or he has also had the option to not attack and proceed. After probe and the attack, he was given the result for each of these rounds, means whether it was honeypot and the web server, and also the scores associated with the actions were computed at the end of the rounds. Likewise, at the end of the cumulative 20 rounds, the adversary was given with the total score for their participation in the game. So for so we for building the computational cognitive models, we used instance-based learning theory, and IBLT and instance-based learning theory has been used previously for modeling the decision making for in the multi-person game scenario. And in IBLT, instance stands for the smallest unit of experience, which is divided into 3 things: situation, decision, and the outcome. And in the IBL model, instances accumulate over time and are retrieved and blended in the memory based on their activation values. So once the activation is nothing but the instance strength, denoting that how much it is likely that needs that particular situation, that particular instance is called to be called, and it indicates the relevance according to the current context. And blending is nothing but aggregation of multiple instances in the memory based on the activation values. And so there are 3 things in the IBIL model: activation, probability of retrieval, and the blending value. So the activation is nothing but the instance strength in the memory, and it has been derived from the actor architecture. And the probability of retrieval is nothing but the probability of retrieving the instance from the memory, and the blending value is nothing but the weighted sum of probability of retrieval and the outcome associated to it. So, in the IPL model, the instance structure for the deception is defined as adversaries, decision, feedback, and the outcome. And we had some pre-populated instances in the in our IPL model where adversaries decision denote basically the web server number and the feedback and the outcome associated to it. So, for example, the web server one may be regular, honeypot, no action, regular means for the web server one, the adversary may take three actions. Either it could be regular, it could be honeypot web server, and either the adversary decides not to choose. So for these three actions, we have the outcome associated to it, and likewise, I will just show you how the IBIL model works for a particular trial in the for the DG. So here, let's suppose the adversary is in the trial one, and the he probes the web server one, and the trial one happens to be deception. Basically, if it just shows him the opposite opposite feedback, means opposite state of the system. So here the web server one happens to be regular, however on probing he gets the as the feedback as a honeypot. So the adversary's mind gets that he is getting minus 70 for this particular action. So and also for at that particular instance we store the timestamp, means denoting at which trial he faced. And similarly, in the attack phase, if he attacks the honeypot, if he attacks the web server one, however, in the attack phase, he gets to know the real, uh, real state of the web server. So here, the web server happens to be the regular one. So here, the outcome is computed as 70 plus 5 for the probe phase and plus 10 for the attack phase. So likewise, the outcome value is computed in the model, and likewise the timestamp also gets updated. So we had built two IBL based model. One is the IBL calibrated and the other one is the IBL ACTA. And here the difference in both these models was the value of D. So we had calibrated the value of D and S. D denoting the memory decay, and the S denoting sigma denoting the noise. And here for the calibrated parameters, we did calibration in the data collected from the human experiment, and for these value we found the D and memory decay and the noise parameter. And for this we used genetic algorithm for optimizing to minimize the minimum square deviation value of the minimum square deviation error. Also, for the actor model, we had set the value of memory decay and the sigma, that is noise, as 0.25 and 0.5 and the 0.25. These are the results of both the models for across all the three conditions, small, medium, and the large condition. And the three model, the both of these model across the three condition, we found that the IBL calibrated performed very excellent compared to that of IBL actor. Like you can see here the currently the MSD values for all the calibrated version of the IBM model was significantly smaller compared to that of actor model. And also we can see from the IBM and the with the and also one observation is that in the across all the three condition, for the medium for the medium condition, the noise was significantly larger, as one of the possible reason could be that there were 50% of them as honeypot and the 50% was regular. So the adversary might have got deceived due to presence of equal version, and on probing or attacking he was not able to predict the good outcomes. So this could be one of the reason for that. And also the memory decay value increased significantly over the across on increasing the proportion of honeypot web servers. Next, these are the result for the both the models, and from the we can see both the IBL calibrated and the IBL actor model are performing similar to what is performing similar across all the three kinds of attack: regular attack, honeypot attack, and the no attack action. Here the x-axis denotes the three condition, and y-axis denotes the proportion of attacks, and the orange denoting the regular, gray the honeypot, and the blue one denoting the not attack action. The left one is for the IBL calibrated model, and the right part shows the IBL actor model results. So we conclude that as with the increase in the proportion of honeypot, we found that the proportion of honeypot probes and attacks also increased, and also we found there was increase in the decay value. So one possible reason could be that the participants got dependent on the recently available informations. Hence, there was a decline in the regular web server attack, and there was increase in the honeypot attacks as the proportion of honeypot increased. So since on probing and attacking honeypots, they in the large condition they were kind of believing the information. So hence they believed that there is a possibility of having honeypot in the web servers and also in the network. And next, also we found that for the small and the large condition, when found that there was a less cognitive noise in their decision compared to that of medium size. So one possible reason could be that as in the smaller and the larger number of honeypot, the environments were consistent. Means one of the web servers happened to be one of the regular was majority, and however in the other condition honeypot was in majority. Hence, the keeping the proportion of honeypot web servers in the network puzzled them or kind of confused them, and they did not and had due to which they it resulted in unexpected response from the network. Hence, from this conclusion, we may conclude that keeping webs number of honeypots in the network around 50% or less than that might be helpful for the cyber for the organization for defending against the cyber attacks. So in future, we would like to evaluate the effectiveness of deception technologies against different types of cyber attacks in the deception game, and also we plan to investigate investigate the presence of different cognitive biases like confirmation bias or any different biases across the adversarial decisions in a cyber situation. Next, we would also like to test with the different combination of deception and non-deception rounds, and how the different deception and non-deception rounds affect in the deception-based security game. And furthermore, we would also like to model the hacker's decision using more different cognitive theories like IBLT, Nango, and various others. So thank you. And in case you have any queries, you may drop me a mail at the email mentioned.